Okay, problem 4, and unfortunately the size of this came out just exactly almost wrong, but we have a conducting sphere with a radius of 5 centimeters, and that conducting sphere has a charge on it. So let me draw our sphere. Okay, so, oh wait, I can do circles. Yay, circle, okay. That's not bad. Whoops, hold on, there we go. That's not bad. Alright, I'll do that, and then I will do a line, and let's just pretend that's a radius. Close enough. Okay, so I'm going to say the radius of the sphere is capital R, and this, my god, this is like the neatest drawing I've ever made already. Okay, and this has a charge of 720 nanocoulombs, which I'm going to call Q. Okay, so this here is Q, and of course this is R, capital R. Duh, right? Radius. Okay, so now we have an electron, and the electron is going to start here, and it starts at the surface with a negligible speed, and we want to know then what is the speed of the electron when it is very far from the sphere, sorry. So there's our electron. Okay, in a way this is the opposite of an escape velocity problem, or escape speed problem. Because instead of saying, well, it's here and it's being attracted to the sphere, how fast does it have to go to escape? Instead, we're saying it's here, it's repelled by the sphere, how fast is it going when it's out here? Okay, so we want to know its speed here. And we know in here, its speed is 0. Okay, so let's call this state 1, and this is state 2. And this is very simply just an energy problem. Okay, so the way to look at this is, let's see, in state 1, you've got potential energy and you've got kinetic energy. Okay, potential energy, you have electrostatic potential energy, that's the only kind you have. And the electrostatic potential energy there is equal to Q times the voltage at this point, whatever it is. Okay, so the voltage here, we're going to call this, well, so the voltage here is the voltage on the surface of the sphere with charge Q, okay? And that voltage, the voltage here on the surface of the sphere, which I will do in purple, why not? The voltage here is K big Q over big R, okay? Voltage on the surface of the sphere is KQ over R, where Q is the charge on the sphere, and R is the radius of the sphere, okay? Simple enough. So, our electrostatic potential energy, that's our voltage, is KQ over R. The electron, now the other thing in here is the charge of the electron, right? So we have, I know I'm going about this a little haphazardly, okay? So this here is V, okay? Now the charge of the electron, well, an electron has the same charge. The electron has a charge of negative E, where E is the elementary charge, and that is 1.6 times 10 to the minus 19 coulombs. So, but for now I'm going to keep it symbolic. I'm going to say this is the charge of the electron, this is the voltage for its initial location, and so the initial potential energy of the whole system is negative KQE over R. Okay? Now the kinetic energy initially, I'm going to just scratch this out so I have a little more space to write the kinetic energy. Kinetic energy initially is, well, initially, and see, this is where bad things happen when you have velocity V and voltage V in the same problem. So this is why I do this sometimes, and I'm going to do it here. Because this V here is a velocity V, or a speed V. This V here is a voltage V. Okay? So now, initial speed of the electron is, or the initial kinetic energy of the electron is 1/2 mv squared. And since it initially has negligible speed, that's 0. Okay? So that takes care of state 1 here. That's state 1 right there. Now, state 2 is when it is very far away. Okay? So, state 2, we have electrostatic potential energy, and we have kinetic energy. Okay, so at state 2, we've got electrostatic potential energy, which is Q times V, and this is Q for the electron and the voltage. Now, the voltage, when you are very far away from this guy, is, well, the voltage is, well, okay, so let's just go with this. The the voltage out here, sorry, let me do this in purple. The voltage out here is kq over little r. So where little r is the distance between the sphere and this point. And we said this is very far away, very far away. So little r is really big. And what happens when little r gets really big is the voltage is effectively zero. That's the convention we use for point charge or spherical charge, voltage field. So this voltage is zero out here, number 2, which then simply means that the potential energy out there is zero. No problem. The kinetic energy at the end is 1/2 mv squared, which is going to be 1/2 times the mass of an electron times the electron's final speed squared. Okay, so now we're at a pretty easy point here where we just do a conservation of mechanical energy. So we do EMEC here is U plus K, which is negative KQE over R. And on this side, EMEC equals U plus K, which is 0 plus 1/2 MEV squared. And since we have no non-conservative forces acting, we can just say mechanical energy is conserved, which then means that negative K big Q E over capital R must equal 1/2 MEV squared. And so what you can see here is this is the initial potential energy. When it has no kinetic energy at the beginning, it has this potential energy. At the end, it has zero potential energy and it has this kinetic energy. So this is still just beginning energy equals end energy. Okay, now this is tricky because we have to remember this E is a subscript here, and that's not always easy with my crappy handwriting. Okay, so what this gets us then, let's take this equation on, is V squared equals, and then I'm going to do a negative, and the 2 is going to come up, 2kq elementary charge divided by mass of the electron times r. And if you want to, you can just and then square root. Now this may bug you. You may be saying, oh my gosh, why do we have the square root of a negative sign? This is going to be an imaginary answer. The universe is broken. Okay, no, we're fine. Because if you remember from the problem, big Q is a negative number. The charge on the sphere is negative in this problem. And that saves us because everything else is positive. So you'll notice that the elementary charge is always positive. Okay, K is positive. Universal constant is positive. 2 is positive. Mass of an electron is positive. Raised to the sphere is positive. But fortunately, Q is negative. Okay, and this also tells us something, which is that if Q is positive, if the sphere had a positive charge, the electron would never escape. And that makes sense, doesn't it, right? Because if the sphere was positively charged, it would be attracting the electron rather than repelling it, and so you'd have an imaginary answer for the electron's speed when it's far away from the sphere because it could never get there. Okay, so the last step really is just to plug things in. So we get V equals square root of 2 times K is 9 times 10 to the 9. All right, 99. Q was negative 270 nanocoulombs. I forget what we said. Oh, 720. Okay, sorry. So negative 720 nanocoulombs, so negative 720, and then nano is times 10 to the negative 9. So I'm just going to make this negative 720 E minus 9. And the charge on an electron is 1.6. Oh, I'm sorry, not the charge on an electron. This is the elementary charge. And it's important because of sign considerations, okay? 1.6 E minus 19. So that is our numerator there. And then our denominator is mass of an electron, which is 9.11 E minus 31.